Yo, what's up, science class fam? Here we go. Coming at you one more time with properties of magnetism. All right, so if we take a look at the science notebook page, we need to put a header here on the left page. You can see we're going to draw some pictures and show three different types of magnets on the left page. On the right, we're going to have some diagrams to understand some properties of magnetism. All right, let's get started. All right, so properties of magnetism. First, let's just define that a material becomes magnetic when all, not some, but all of the billions of atoms that are within the substance align in an overall, something that we call a preferred orientation. Now, the preferred orientation doesn't mean they all have to be left or right. I'm going to put quotations around it because preferred can mean a lot of different things. But if we zoom in on like a rock, maybe we have like a rock here, a piece of iron, or actually let's say this is just a piece of granite, which is non-magnetic. If we were to zoom into a little part, that's kind of what we're looking at here in this picture here with all these atoms. So an atom has a nucleus, as you learned in 6th grade, and it has electrons that are kind of orbiting it. Now, as it aligns with other and interacts with other atoms, it actually starts to have this distribution of charges. And we'll learn more about this in our micromagnetism science notebook page a little bit later on in the unit. But essentially, if you look at the atoms are going to have a positive and a negative charge. And sometimes the positive and the negative charge is aligned, and sometimes it's not. Sometimes it's the opposite. Sometimes it would be one direction, and another time it could be the opposite direction. So in this example here, we're going to show a non-magnetic substance. And in these non-magnetic substances, the orientation is in just a random cluster. So you can see the positives and negatives are sometimes on the top, sometimes they're on the bottom. And that's different than a magnetic substance. So let's say we had a nice shiny piece of iron over here, and we zoom into a little piece of that iron and we look at the atoms in the iron. Now, if we zoom into the atoms on a magnetic substance, all of the negative charges are going to be near each other, and all the positive charges will be on the opposite side. But when we compare how the top layer of atoms aligns with the next layer of atoms, the positive will be attracted to the negative atom, the negative portion of the atom below it. So we find this preferred orientation where there's a very distinct pattern of orientation, which that one would be wrong because we need a negative charge. So let me back up there. All right, negative, positive, and positive. So you can see over here we end up with an overall negative charge, positive charge, negative charge, positive charge, negative charge, positive charge. And so we end up with a magnetic substance. So this one we could say is organized. Therefore, it is magnetic. This one on the left, we could say that this one then is disorganized. And this one would be non-magnetic. Okay, so we see what it takes on the atomic level for something to be magnetic or non-magnetic. And there's actually different types of magnets, so there's different ways that things can become magnetic. And as we go through these, I'm sure that you'll be able to relate, and you've experienced some of these in your lives. So a ferromagnet, this is when all atoms are always aligned. So these are what we would call then permanent magnets. So they're always magnetic. It's like the classic magnet that you see, whenever someone draws a magnet, a bar magnet here is my example, where there's an N on one side and an S on the other, a north and a south pole on the magnet. These ones are always magnetic. It's never not magnetic, but we find that there's actually some substances that are magnetic sometimes, but not all the time. So this isn't one of those. This is always magnetic. It's a permanent magnet. All right. Well, if we go down to a different type of magnet, this is another one that you're probably familiar with as well. And so you can kind of get a preview there of my refrigerator. I'm going to switch the color here and kind of get something new. So a paramagnet is when atoms align only when they're in the presence of a magnet. So a paramagnet is when the atoms align only when they're in the presence of a magnet. So the atoms actually have the ability to kind of shift within the material, which is kind of crazy to think about. If you have a solid substance, we don't generally consider the fact that the atoms are moving around, even though it's a solid, but they do have the ability to actually reorganize themselves. So an example of that would be magnetic metals. So like a paperclip. A paperclip can attach to a magnet, and so it is actually what we'd call a magnet. The metal on your refrigerator, it's not magnetic. You can't just put a paper clip on it and have it stick. That's not going to happen. But if you do have a magnet, the magnet sticks to the metal because the metal becomes magnetic, and then you can hang up your homework that you get that 4 on, or the A+ or whatever. Or you can hang up with a magnet your awesome happy tree picture, whatever that might be. But that metal on the refrigerator, or it could be a filing cabinet, or just any type of metal that is magnetic, that would be actually considered a paramagnet, because the atoms will reorient themselves to all have them all aligned in that preferred orientation, but only when there's a magnet present, a permanent magnet present, or a ferromagnet present. So there's one last type of magnet though. This one is an electromagnet. So in an electromagnet, a wire must be wrapped around a metal core. And this causes the atoms to align with each other in that preferred orientation. So down here, you have to have a power source. I've got my battery down here, and I'll attach a metal wire to it. We'll use a copper wire because that transfers the electricity really well. And it will wrap that around the nail. And when it is wrapped around the nail, all of a sudden, it can then have paper clips that are then attracted to it. And if we disconnect the wire, and all of a sudden the wire is no longer attached, the electricity can't flow through the wire anymore, and we don't have the attraction happen anymore. It actually turns off the magnet. So the electricity is required, and that would be why it is called an electromagnet, because you have to have electricity flowing through the wire, which is wrapped around an iron core, and then it becomes magnetic, and that is an electromagnet. If you look in the SciFlix, you can actually find some videos of some pretty cool, pretty strong electromagnets. Take a look. All right, let's turn the page, and let's now draw some diagrams to kind of show some of the relationships and some of the behaviors that we find happen when we have magnets or magnetic fields. So as I discussed before, this is a bar magnet. This one is your ferromagnet, the one that's always magnetic. And we're going to put the north pole of the magnet up on the top and the south pole of the magnet at the bottom. And so it'll become more obvious why we're using this north and south pole now at this point, because what we find is that when we have a magnet, we have a magnetic field that starts to form around the magnet. The way that the magnetic field starts to form is that the magnetic field travels from the north down to the south pole, and then it enters at the south pole. So we end up getting this arc type of, or this bubble kind of thing around a magnet. And as you get further away, you can imagine that the power of the magnet starts to decrease. The force of the magnet starts to decrease as you go further and further away. So I could maybe draw one way out there because it's way less than it is as you get closer. Okay, well, we have this magnetic field happening around the magnet. And so if we place two magnets next to each other here, and we have our north poles here at the top and our south poles here at the bottom, we have the same poles next to each other. And when you have the same poles next to each other, then as you may have seen, or I'm sure you've played with magnets before, they repel each other. Same poles repel each other. So let's draw some arrows here above these magnets and show they're going to actually push apart from each other. It's not just the north poles that are going to, but the south poles repel each other as well. Now, if we put opposite poles near each other, That means we have the north pole on one magnet and the south pole on that same magnet in this orientation. The other one then would be flipped. So actually I should erase this kind of shading here to show that this is now the north and that's the south. And when we have magnets that have opposite poles next to each other, they become attracted. Opposite poles are attracted to each other. So opposites attract with magnets, and the same poles will repel each other with magnets. Now, let's think about this. This is actually kind of interesting and kind of crazy. Maybe it could blow your mind a little bit right here. So that means then, if we have a magnet, and let's say we have a compass right here next to it. This is my compass. And I'm curious, well, which way is my compass going to point if I'm next to a magnet and it's going to point towards the north? If opposites attract, then if this needle is attracted to the north, or if it's a north, if this is a north pole needle, it's going to be attracted to the south pole of the magnet. So it's actually going to tell me that the north pole is down here. I know, weird, and opposite and backwards. But if opposite poles attract, then our magnets are actually telling us where the south pole of the magnet is, but that's what we call on a compass. This is what we would call the north pole. So when we read the compass and we move towards the north pole, we're actually moving toward the southern end of the compass. So let's look at the Earth and really break this down. So if we have a magnet here within the Earth, the inner core of our Earth creates a magnetic field. So we end up with this north-south type of magnetic field where the charges are moving from the north into the south, from the north into the south, and so on and so forth. And this creates a magnetic field here on Earth. Well, as you can see, I've already drawn the north pole, the magnetic north pole that we call it as humans, as we're on the surface of the Earth. So we can imagine then that if we bring a compass into this setting, we can imagine, let me draw my compass here. I've got my compass circle right here, and if I were to find where the North Pole is going to be, well, let's just draw, it's going to point towards the North Pole here, but you can see that the magnetic pole, or the magnetic force lines are pointed towards the North Pole, magnetic North Pole, but in the magnet, it's actually the South Pole of the magnet. So again, if this person's down here in the southern hemisphere and it's going to point, their magnet's going to point towards, or their compass is going to point towards the north, it's going to point up in this direction because it's going to align with the magnetic field, and it's going to be attracted in this direction. So it's going to point that north is up. But really, on the Earth, if you were to actually look at the actual magnet, if we had a bar magnet in the middle of the Earth, which it's not truly a bar magnet, but it would actually be what we would say is the south pole of the magnet, but it's the geographic north pole. It's a little bit backwards, but you can remember this when you think about two magnets. The opposites are going to attract each other, and the same poles are going to repel each other. So if you have a compass, the compass is going to respond to those magnetic fields, and it's going to align with these arrows, and you can see the arrow's force, the arrow's direction is this direction. So if we then turn that into a compass, that's going to point to what we say is the north, because whenever we look at a compass, we always look at where the arrow is pointing, and we call that the north. So again, here, this one would point here is going to be where the north is because it aligns with that magnetic field line. All right, well, if I blew your mind, please put it back together and move on the Sci-Hub, and I'll see you here in just a little bit on the next Science Notebook pages. All right, see ya.